Okay, folks, one more video on optimization. Who knows, there may be more to follow. You can let me know how much you love these videos. This is a fencing problem. They are extremely popular. One of the first things that we talked about when we talked about optimization was the fact that if you want to optimize an area, a rectangular area, the answer is always a square. So they know that we know that, and because they know that we know that, they screw with us. This is one of the ways they screw with us. I already had mentioned that sometimes they'll have you fence in a rectangular area, but you don't need one of the sides. So there's problems where you're fencing in an area, but like around next to like a barn or a building or something, so that one side of fence you don't need because the building is providing that barrier. There's one where you're fencing an area along a river, so the river provides one of the sides. Anytime you've got not four sides involved, you're going to have not a square as your answer. And this is one of the ways they do it, where they have us do a rectangular area but divide it into sections. And the number of sections they have us divided into really doesn't matter. The premise of the problem is the same. So in this problem, they tell us we have a 216 square meter rectangular pea patch. That's very important. They're growing peas. And it's to be enclosed by a fence and divided into two equal parts by another fence parallel to one of the sides. So you can see in the picture I drew there, I have a rectangular area cut in half by a fifth piece of fencing. They want to know what dimensions for the outer rectangle will require the smallest total length of fence. So in case you ever wondered where you're going to use calculus in real life, it's to save money, because you want to use the least fence possible, because fence is expensive. Trust me, I know. All right, so the first thing we're going to do is identify our restriction and our optimization. So when you read the problem, 216 square meter pea patch. Okay, there's our restriction right there. The area of this thing has to be 216 square meters. As far as optimizing, that's where our last sentence comes in. The one with the question mark is usually a good hint. And remember, we're looking for keywords like smallest, largest, biggest, littlest, most, least. The smallest total length of fence. So it is the length of fence. I'm kind of thinking of it would be perimeter if it weren't for this line down the middle. So it's kind of a perimeter type thing, but kind of not technically the perimeter. Okay, so the next thing I need to do, because I'm going to need to write equations for area and length of fence, is to define some variables up here in this diagram. So I'm going to define x as the side-to-side measurement of the pen and y as the up and down measurement. So as far as my fencing goes, I'm going to need two lengths that are x long, and I'll need three lengths that are y long, one to go up each side and one to go up the middle. Okay, so my area should be pretty simple. It's just going to be x times y. It's the area of a rectangle. So my restriction is that xy has to equal 216. We know we'll be using that here in a few minutes. Okay. As far as the length of my fence, like I just said, we're going to have two lengths of x and three lengths of y. And so the length of my fence is going to be two x's and three y's. And like we talked about in every single one of these problems, at this point, I've got two problems with this equation I'm trying to optimize. The first is that it has two variables, both an x and a y. That's a no-go. Unless you're doing a related rate with implicit differentiation, you should not have more than one variable in your equation. The second problem I have is that I have not incorporated my restriction. So let's do that. Incorporating your restriction is going to solve both of the problems over here. So I chose, because I like solving equations that are in terms of x, that's just who I am as a person, I chose to take my area equation and solve it for y. So if you take xy equals 216, solve it for y, you get 216 over x, and then I'm just going to come over here and plug that in, do a little system of equations for y. So now the length of my fence is 2x plus 3 times 216 over y, which simplifies a bit to 648 over x, plus 2x, of course. Okay, so here's my setup. Here's my model. This is the model for the length of my fence. Depending on what x is, this is the length of fence that I will need, right? So if I decide that my pen is going to be 10 long, then I can figure out my length of fence here. Now, what we want to do though is figure out what is going to minimize this length of fence. So I need to minimize this model. So here we go. To minimize, we're going to take the derivative, we're going to set it equal to 0. Remember, it doesn't matter if you are minimizing or maximizing. The process is the same. That's why we call it optimization, right? It's going to, the answers when we do this are going to give you the greatest and the least. Right? So if you get 2 answers, then of course you need a sign chart. You have to check and see which one's the min and which one's the max. But if you just get 1, and if you did everything right, then it should be the one you need. Can't hurt to check, but it should be the one you need. Okay, so to optimize this, we're going to take its derivative. It's a pretty simple derivative and set it equal to 0. So the derivative of 2x is 2. The derivative of 648 over x, you could rewrite that as, please don't use the quotient rule, you could rewrite that as 648 times x to the negative 1, and it's a much simpler derivative. And you get 2 minus 648 over x squared. Again, if you rewrite this as 648 to the x to the negative 1, it becomes negative 648 x to the negative 2, and then you can just pop that back downstairs again. And that's equal to 0. This is a pretty simple solve, so let's get it solved. I'm going to move one term to the other side so that I can do a quick cross multiplication. So if I did a little switcheroo here to avoid having some negatives, right? But it's 648 over x squared has to equal 2, right? In order for this equation to equal 0. So I can do a quick cross multiply. I end up with 2x squared equals 648. And then that's our real quick quadratic solve. So I'm going to divide both sides by 2. I get 324. And I'm not going to lie, I put this in my calculator, even though I should probably have this memorized. My x has to be 18 meters. Now again, it's a square root problem, so technically there's 2 answers here, right? Positive and negative 18, but that's ridiculous because you can't have a negative length. So we toss out the negative 18. It's an extraneous solution. It doesn't count towards this problem. So because this is a real life problem. So I know that my x has to be 18 meters. So once I know what my x is, I can figure out what my y is, because I know that y has to be 216 divided by 18. So my y must be 12. So this thing has to be 8, whoops, sorry. This thing has to be 18 on this side, and then 12 this way. So these individual squares, they look like squares, but they're not. They're 9 by 12. And that gives us our maximum area. So again, you see lots of variations of this problem, lots of different, they take a side out by providing some other way to close something in, or they put partitions, but it's just iterations of the same idea. They're either going to give you a fixed perimeter and have you maximize or minimize, well, not minimize area. Usually you're maximizing area, right? They're going to give you a fixed perimeter or a fixed amount of material that you can use and ask you to maximize the area, or something like this where they give you a fixed area and then ask you to minimize the material you're using, right? Because we're always trying to get the most out of the least. That's what we do. All right. Let me know if you want some more videos. I love talking about calculus. See you soon.